All right, Monte Carlo integration. So we saw before when we were trying to calculate an integral numerically that life got really hard in low dimensions. And Monte Carlo integration is a clever way around that. But it takes a while to understand this. This is essentially what particle filters do, is use Monte Carlo integration to overcome that dimensionality problem of numerical integration. So just an outline, an overview of the slides. All right. So based on what we were just talking about, I don't need to emphasize the fact that we've got this integral here, and that was really the bottleneck, the computational bottleneck, when we were trying to do optimal tracking in more than one dimension. So though this set of recursions, it's beautiful, it's elegant, you can write it with two equations, you can explain every term and make sense of it. We can't do it analytically in most cases. The only times when you can do this is when you've got a parametric distribution, parametric description of the posterior, and you're able to crank through the math to figure out how to track how that posterior is changing over time. The Kalman filter in the linear case essentially does that where the posterior is Gaussian, and it tracks the variance and the mean of that distribution, and that's all you need. Or I should say the covariance, since we're talking about a vector. Numerical doesn't work, and Monte Carlo integration is arguably a way out of this pickle. So let me take a little bit of time to explain what it is. Most of this set of slides is going to be about the concept, and we'll talk about how to apply this concept for state space problems in the next set of slides. You can see I've dropped the time index right here, and that's deliberate. It just makes the notation a little bit easier to explain the concept. And I'll be going through these equations is treating it as though x is a scalar and mu is a scalar, but everything I'm talking about generalizes to the vector case. So if you want to think about it as a vector, you can. If you want to think about it as a scalar initially when you're learning this, that's fine too. So one way of thinking about this integral, you can see that I've said, okay, well let's consider there's an integral that we're trying to calculate. We want to figure out what the integral is of some function g of x, and I'm calling the result mu. You're like, well, wait a minute. Mu is usually used to denote the mean of something. Why are you doing that? That's weird. And the answer is that these Monte Carlo techniques, it's really clever. They take the thing we're trying to integrate and they factor it into two different components. So we have a background in signal processing. We're used to breaking things up into their components. That's kind of what the Fourier transform is, breaking a signal up into a sum of sinusoids. In this case, we're factoring g of x into a product of two different functions. So g of x is equal to a product of f of x and p of x, and you get to pick what p of x is. Once you've got p of x, then f of x has got to be the ratio of the two. P of x is going to be a PDF. It'll be a probability density function. So you're going to pick some PDF p of x, so and I don't have this quite on the slide, but this only works if p of x has to be, let's say it's always greater than or equal to 0, but it's got to be greater than 0 wherever f of x is greater than 0. So p of x has to have the same support as, g of x. Wherever g of x is greater than 0, then your PDF has also got to be greater than 0, because otherwise this breaks down. You can't have g of x is equal to f of x times p of x if p of x is equal to 0 at those points. So it's a small point, but that's one of the things we got to have. And the neat thing about this, sort of the voodoo that happens here is, I guess I need another equation to make this clear, but once we've done this factor, then that means mu can also be written as the integral of f of x, p of x, dx. And if you look at that closely, and knowing that p of x is a PDF, another way of looking at this is the expected value of f of x. You see that? It's like, that's weird. So now you understand why I used mu here. This is really the mean of this function f of x that we made up. Is that okay so far? So, so we're kind of going backwards. Normally you say, I want the expected value of something, and you do a little bit of math, and you end up with an integral of that thing times the PDF, and you integrate over the random variable. But in this case, we went the other way. We started off with an integral, and we're ending up with an expectation. Again, you get to pick the PDF that you're going to use. It's got to be, being a PDF, it's got to be greater than or equal to 0. It's got to have unit area, but you get to pick it. So, like, again, that's fine. So we're trying to find an integral, and now you're telling me I can think of that as an expectation. That gets us part of the way there. The next step is, let's say this PDF that we chose is something that we can draw samples from. So we've got a random number generator. Let's say we chose a uniform distribution. There's lots of uniform random number generators, so it would be very easy for us to draw a lot of samples from that random number generator. So let's say that we can do that. We can draw a large number. And if we can evaluate f of x at each one of those samples, and I'm using a superscript not to denote a power, but to denote a sample index, because I'm going to use the subscript to denote time, right? I mean, that's what we've been using, and other things. We just run out of places to put things. We end up with like accent marks and superscripts and subscripts. So this superscript, I'll do this consistently. In this case, is not a power, it's an index of the sample. So we've got the ith sample. Later that'll become the ith particle, but right now it's the ith sample. And if we plug that into f of x and we take a sample average, then we can get an estimate of the mean. But the mean, you'll recall, was the integral. So the way Monte Carlo integration works is, and I hate this, I was strongly objected to this on principle as a graduate student myself. I'm like, we should not be doing computation with random number generators. That's absolutely the wrong thing to do. And now here I am, ironically, a professor many years later teaching a course about using random number generators to do computation. So we've got a random number generator, we plug it into our function, we calculate a sample average, and we get an estimate of the mean. And this is basically what Monte Carlo integration does, and it's the basis of particle filters. Particle filters are driven, as sad as it is to me, by random number generators. So now, really, instead of computing the integral, we're estimating the integral with a sample average. Yeah, you guys seem remarkably cool with that. Like, it took me a long time to accept that idea. You guys are fine with that? Okay. When we look at this estimate, mu in, where n denotes the number of samples that we've used to calculate this average, it turns out this is an unbiased estimate of the mean, which is good. We talked about bias and variance briefly before. So when you're thinking about an estimate now, we've got the hat. This is not the true mean, it's an estimate of the mean. So we want to ask about its statistical properties. And I'll tell you about its bias, its variance, and convergence. So it turns out this is unbiased. That's good. All other things being equal, we prefer biased over, or unbiased over biased. Another nice property it has is that it will almost surely converge to the mean in the limit. This is an asymptotic result. For those of you that have studied probability, there's many different forms of convergence. This is just one of them. As engineers, we don't really care. We're like, does it converge or not? Like, I don't care by what criteria, if it converges in probability or almost surely or mean squared error. Like, it just doesn't matter for most engineering applications. So if you get any of those convergences, you're happy. And we got one. It converges almost surely. And I won't take the time to go through and tell you exactly what that means. But basically, in the limit is you have an infinite number of samples. The probability of there being any difference between those two goes to 0. Or the probability that they become equal is equal to 1. There's a couple different ways of looking at that. You can Google almost surely if you want to know more about that type of convergence, or read the reference I gave you. And then, did I skip a slide? I'll come back to the variance. So, as an example, do any of you have the slides in front of you?
Yeah.
Did I skip one?
Just now? No.
Okay, great. So variance is coming. Sorry, stay tuned for variance. It's in a later slide. I thought it was the next slide, but it's later.
Next one is error convergence, and then cursive dimensionality.
Great, we'll get there. Thank you very much.
Yeah.
So for now, as an example, let's say that we use a uniform distribution, in part because it has constant support over an entire range. So as long as if we're doing a definite integral and we know what the limits are, then we can just set that equal to a constant. It's very easy to do. And uniform random number generators, even in high dimensions, are readily available and mature and very good. And delta, of course, is x max minus x min to ensure that this has unit area. So this is a uniform distribution. If we plug that in, and now I've said, let's assume our integral is definite, so we're only integrating from x min to x max. We factor g of x as being some function f of x times 1 over delta. That only works if g of x is equal to delta times, or I'm sorry, if f of x is equal to delta times g of x, as I have down here. But once we have that, then sure enough, the integral we're trying to calculate can be expressed as an expectation of this function f of x. And so then we can draw samples from this and take the average, and we'll get our estimate of what the mean is. So this is a one-dimensional example for the uniform case. I'm sorry, these slides are not going where I thought they would quite. If the variance of g of x, or equivalently the variance of f of x is finite, where the variance of f of x is defined this way, we already know how the mean is defined, and if you take the expected value of the function minus its mean, then you get the variance. If that's finite, it only has to be finite, and basically all the functions that we would encounter as engineers are finite, then it turns out the central limit theorem holds, and I actually won't show you the details later, but you can find it in the reference I provided. Then it turns out that we can have a tighter form of convergence, and in the limit as n starts to become really large, then the square root of n times the difference between these two ends up having a normal distribution with a variance that is constant.
What does it mean for g of x to have a variance, since it isn't defined as a random variable?
Yeah, I almost changed that in these slides, and put in variance of f instead, because that is well defined.
Does that just mean it has compact support?
I should have said that. So sigma, it means that this integral is finite. Okay. And you could plug in g of x, or substitute in g of x after you calculate what it is from f of x, and then end up with something like that. But I'm sorry, I probably just should have said as long as the variance of f of x is finite. So the error of this estimate, the difference between those means, ends up having, the standard deviation of that error ends up being on the order of 1 over the square root of n. And so this converges somewhat slowly, but the biggest part of this story is that when you look at the convergence, if we draw a lot of samples, we estimate the mean, the error variance, I'm saying variance instead of standard deviation now, and so it's ordered 1 over n instead of 1 over square root of n. But the variance converges at that rate. And the big news here is that this doesn't depend on the dimension of the thing that you're integrating. So if we're integrating this super high dimensional thing, and you're doing Monte Carlo integration to estimate what that integral is, the rate of convergence doesn't depend on dimension. It only depends on the number of samples that you're using for the integral. That's why, that saves us. It's a big deal. And so it would seem that we're way better off doing this. We have to throw random samples and do a random number generator, but cycles are cheap on computers, and we've got lots of processors, thanks to Colin, And so we can generate a lot of samples independently, and getting a big N is just not hard for us, as long as that N doesn't have to scale exponentially with dimension, as it had to when we were talking about numerical integration. So it looks like we've won. We've had a victory over the curse of dimensionality, and I'll talk more about this later this term. You know, I've got the or does it. There's much more to the story. The curse is a really hard thing to beat, and so it may be that victory is being declared a little prematurely here, but at least in principle, we've got something promising that you probably won't ever see anything else that allegedly beats the curse of dimensionality, because it's just hard to do anything in high dimensions.
Do you pretty much almost always factor out the uniform distribution? Because it seems like that would be easy to...
No.
No.
Stay tuned, you'll see. But it'll turn out for putting this in a state space framework, a state space tracking framework, the uniform distribution is going to turn out to be about the worst thing you could do. I'll explain why when we talk about the particle filters.
Wouldn't the uniform distribution be equivalent of like using n bins and calculating, you know, the grid-wise integral? It's the same thing, like you sum over all those bins, right? So I don't see how, like at least for the single dimension, I don't see how this is beneficial.
Yeah. Well, and in a single dimension, I argued do optimal tracking. If you've got a single dimensional tracking problem, do the numerical integration. You're right, this is not advantageous in low dimensions. But when you go to higher dimensions, you can also do a uniform distribution. Like if you were doing it in 2 dimensions, you would be putting basically points in a plane.
Won't we need more points? Like n won't increase with number of dimensions?
Well, that's kind of the question. I mean, that's why I'm saying, or does it? One answer is no. The answer is suggested on the slide, and the answer, I don't want to get into too much depth here, but the basic answer is no, because look, we're just trying to calculate a mean. We're not really trying to evaluate this function over a dense number of points in the high dimensional space. We're just trying to figure out what its average is. And if all you care about is its average, then you probably don't need to sample every single point. You know, a lot of those aren't going to contribute that much. After you get to a big enough N, adding more points isn't really adding that much, probably, maybe. And, you know, I mean, that's where we'll talk more about it. But at least in principle, you can make an argument that if you've got if you've got like a big Gaussian posterior, then you draw 500 samples from that, you're good. It doesn't matter if you're in 1 dimension or 20.
Right. So it looks like the gain actually will come from choosing the right value of P, or form of px, not from the bins. Like if you use uniform, n samples here will be equivalent of n bins, in the flat integration.
Yeah, that's true. But it's only equivalent in 1 dimension. When you go to higher dimensions,
even in 2 dimensions, we can have like n square, n squares. It will have the same value as n samples here.
Okay, imagine trying to fill a cube though. I mean, now you're like, oh my gosh, to get every single bin, I've got to have, I've got 100 bins on a slide, I now need, 10,000 times 100, you need 1 million. You need 1 million bins. But you can also imagine just putting points randomly in that cube.
Right.
You're like, well, if I fill it with 1,000 points, I'm probably going to fill it well enough that I can estimate the mean for my purposes, even though I haven't densely packed that thing. Even in 3-dimensional uniform distribution. Yeah, so as you go up in higher dimensions, you can make the argument that, you probably don't need, this probably doesn't need to scale that much with dimension, not nearly as much as you would if you're doing it numerically, even in the uniform case. I mean, it does depend on what you're integrating, but for that probability, yeah. So we've got something that looks promising, and it works well enough that it's worth making it the highlight, the sort of star of the show of this class. So it's not worthless. It does work well. It's not always the right thing, but it's worth teaching to. So let's talk about an example. Suppose we've got again a cosine. It's a signal processing class. There's lots of cosines and sines, and in this case, the integral is already expressed as a probability, and I'm expressing it as though our goal is already to calculate an expectation. So I'm going to take the expected value of a cosine where we're taking a cosine of v, where v is drawn from a normal distribution. So when you say, okay, my goal is to calculate the expectation, that turns out to be an integral, maybe I can do that with Monte Carlo integration. You can do it numerically as well because it's easy, it's one-dimensional problem, but I could have made this a multi-dimensional problem, and then you would have been stuck if you tried to do it numerically. So one way to approach this is to say, let me draw samples from a normal distribution. There are Gaussian random number generators are very easy to find. They're all over the place too. And it's easy to calculate Gaussian random variables with any mean and variance you want. So I'm just going to grab a pile of those and put them into a cosine, get the output, and calculate the average. I'm going to use that as an estimate of what this integral would be. Does that make sense? All right, so let's see how well that works. So here's a plot, and what I'm plotting is a running estimate of the expected value of y based on this Monte Carlo integration technique. The red line is showing what the true mean is, and I know what it is in this case, or I computed it. I guess I estimated it by numerical integration. But the Monte Carlo estimate is shown by the blue. And you can see, initially it's way off, huge variance initially, but after I have just a few samples, it gets in there and it's pretty tight. And then it's good, and it kind of wanders off a little bit, and then comes back in, and then wanders away again, and comes back in. But it's getting there. It's not bad. It's pretty close. It's off a little bit, but it's not off that bad. Worked, kind of. All right, so we're like, great. We've got a way of beating the curse of dimensionality. We know what the integral is we want to evaluate. Go. Do the Monte Carlo integration. Like, we're good to go. And so if you were to try to apply this technique we just talked about directly to this prediction step of the optimal recursions, the problem that you'd run into is you say, okay, this is already in the form of the integral we need. There's a probability right here. It's conditional probability, but it's still a probability. And the function in this case is our prior, which is kind of cute. And all we have to do in order to be able to do Monte Carlo integration is draw samples from this. So all we have to do is draw samples from this. And then we can calculate a sample average, and we'll get our output. The problem with that approach is that you can't draw samples from this thing. Even if we know what this is the posterior distribution. And you saw it in the one-dimensional case. We were estimating that thing directly. I mean, you're doing this for your homework on Thursday. You're going to have plots of what that posterior looks like. But being able to evaluate the posterior at every one of those 400 bends is different than being able to draw samples from it. And some of you may have said, well, look, I learned in my statistics class or your probability class that there are techniques by which you can draw samples from an arbitrary probability, and there are, but don't try doing that in a high dimension, which is what we're trying to do. We're in a high-dimensional space for most of our tracking applications. So we hit a brick wall here. You're kind of stuck right now. You couldn't just apply what I've taught you so far and suddenly be able to do tracking. We're not quite done yet. So in general, Monte Carlo integration requires that we're able to draw samples from the probability that we chose. And we couldn't quite do that directly. In general, you may have a probability like what we're going to have where you can evaluate that probability at any given point, but being able to evaluate it at a point and being able to draw samples from it are completely different problems. So what do? We pick a different PDF. Rather than picking the P of X that's kind of shown here, let's say we pick a different one. And this is the only PDF that I'm going to represent with a letter other than P. But it's because P of X and Q of X, I mean, they're always going together. We're using them together a lot. So there's this other thing that is called an importance density. It's just a PDF, but it's an importance density. And it basically represents the PDF that we can draw random numbers from. So I'm going to introduce this idea of we can't draw, we ended up with a factoring that was very nice, but we ended up with a PDF we couldn't draw numbers from. But now I've got this other PDF that we can draw random numbers from. And so let's work with that. So this, again, is called an importance density. It's denoted as Q of x throughout all the, this is one thing that's consistent in all the literature I've given you. In my notes, they always use Q for some reason to represent this. And if we go back to our original problem, and now we factor it a little bit differently, we say, okay, this whole thing we're going to leave, but now we've got an importance density, and we're going to divide this by Q of x, multiply this by Q of x, and now we're trying to take the expected value of this entire thing. And so we draw samples from Q of x, and now we have to evaluate the sample average of this whole thing, our function multiplied by P of x divided by Q of x. And I'm going to call that ratio a weight. Particle filters have weights. These are the weights. It's the ratio of the PDF we wanted to draw samples from divided by the PDF we could actually draw samples from. They're never the same because we can't draw samples from this. For us, it's the posterior, but we could draw samples from this. And the ratio of those PDFs are weights. I've got this little tilde right now because, as you'll see, this is unnormalized, and when we normalize it, that's the one we normally work with, and so the tilde will go away in a while. For now, just treat this as a definition of those probabilities. So we do this, where I've defined the weights as, again, the ratio of those two. We can usually evaluate both the PDF that we drew numbers from and the PDF we wanted to draw numbers from. We can evaluate both of those at any given point, as well as the function that we are working with. So all these can be evaluated at an arbitrary point, but we can only draw samples from Q. And so we end up taking the sample average of not just the function, but the function multiplied by these weights. Again, Q of x is going to have support everywhere that P of x has support, but that's a relatively minor point right now. So let's see how this works. Let's suppose we've got the same example we had before, but there's a key difference now. Let's say we don't have a normally distributed random number generator. The only thing we're stuck with is a uniform random number generator. Unfortunately, cosine is a bounded function, and so we can draw uniform numbers between -1 and 1 and cover the whole range of the integral. But now we have to do it with a uniform distribution and use this weighted technique. This is what happens. This is only a single realization, but you can see there's high variance. And if you remember, or if you happen to have the notes in front of you and you look back, you can see this takes longer to converge to the true mean. The other one was pretty close within a small number of samples. I think after about 100, maybe 50, it was close. This one got close, but then it wandered away, and then it kind of came back. So this one had more variance, or would have more variance on average. This is just one realization, but you can kind of infer from this that this isn't a special case, and on average there would be more variance. So this converges more slowly. Still converges, but converges slowly. Are you guys spent? You guys with me still? Is it okay? Just a little more. I'll find a good stopping point here in a second.
What's the intuition behind importance? Or why is it importance simply?
Why did they use the word importance? I don't know. What?
Because likelihood was taken.
Well, no, likelihood has a very different meaning.
I know. The word was taken, so they had to call something else.
Yeah. I don't know the etymology of that. I don't know the history of that or why they chose that. But Colin, you asked another good question earlier, and you were asking about this term, and that's a term now that we can start to deal with. As I emphasized earlier, the effect of this term, one way of treating this term is it's really equal to the integral of this times that. If you do a little bit of math and apply Bayes' rule in the right way and integrate this, or look at this, ends up being the same thing, and you integrate that, it ends up being equal to the denominator. And so one way of thinking about this is the only thing this does is normalize this whole expression so that this has unit area. And there's another way of doing that with these, with the weights, and the way we're doing this now with Monte Carlo integration. So, and the reason for this, and I know I haven't explained this quite yet, but the motivation for this is that what particle filters are going to give us is not quite the posterior, whether you're looking at this equation or this equation. We won't quite get the posterior, we'll get something that's proportional to the posterior. And so it'll be off by a scale factor, but as long as we can normalize it, we don't care. And it turns out to be a very simple way to normalize it. So again, instead of imagining that we've got the PDF that we want to draw samples from, but we can't draw samples from it, but we can evaluate it at any given point, I'm going to make it a little worse now and say, let's say we don't actually have P of x, but we've got something that's proportional to P of x. So we've got this kind of P tilde, and that screws everything up until you correct for it. If you calculate the mean, of course, it's going to be biased. That constant factor ends up coming out of your, or showing up in your calculation. So we need to correct for that. And it turns out that, with our samples, one thing we could do quite easily is we could say, well, let's say that we're just trying to take the expected value of f of x, where f of x is a constant, where it's not actually a function of our random variable, but it's just equal to 1. The expected value of 1 is 1. And so one of the things we can do is we can say, well, if we go through and evaluate all this with f of x is equal to 1, then the mean that we would compute, if we didn't do anything else, ends up being equal to that constant. And so, so we can calculate that constant by essentially by this expression. And the trick by which we essentially derive that is by taking the expected value of 1. We know what the answer is in that case, and instead what we end up with is the constant by which we were off. So if we then take our estimate of the mean and divide it by this constant, we'll get rid of that bias and we'll become unbiased. So the way the weights are normalized in general then is we calculate the mean, we go through, we calculate this average, but then we divide by that same average of the unnormalized weights. That's essentially all we're doing. And you can look at this a couple different ways. You can say, oh, well, these cancel, the 1 over n terms cancel, and I can change the variable summation from I to j, because I'm going to move it into the upper term. So that gets us from this equation to this equation, and now this is the variable summation is j, so this whole term can be treated as a constant, and I can move it into that sum. And so we end up with the sum of our function times the unnormalized weights divided by this sum. And that can be written as the weighted sum where we're using normalized weights, where the normalized weights are defined this way. So when you get your weights, all you have to do is divide by the sum of the weights, and suddenly they're normalized, and we no longer have to worry about that scaling constant. So that's the weight normalization step. Is that okay? So cute. That solved one of the problems that we had. And I think this is probably a good stopping point, because there's one other big idea in this set of slides, but I don't have enough time to explain it fully. So we'll talk about thinking of probabilities as sums of impulse functions first thing on Thursday.